Hi, everybody. I'm Aaron. I'll introduce myself first. I'm a senior staff software engineer at Google. I've been there since 2008. Worked on a bunch of different things, mostly C++ backend stuff. Some things I can name drop publicly are the Google Maps API, Google Cloud Storage, Bigtable. Also a bunch of other storage-related work behind the scenes, as well as more general infrastructure kind of stuff. And I'm here today to tell you about some design decisions I made while I was designing a coroutine library for use in Google. So I'll start with an overview of what we're going to talk about. We'll begin with things that are weird about Google, and then I'll talk about the two sorts of scale that we're interested in here. That's both efficiency and the ability to scale to thousands of engineers using the library easily. After that, I'll show the basics of what the coroutine library looks like. And then we'll dive into the deeper technical parts. We'll talk about lifetime rules for coroutine parameters, bounding stack usage of the coroutine library, and implementing really good cancellation support. Let me start by giving you a snapshot of where we are with coroutines inside Google. We turned on C++20 for most builds last year, although I've been using coroutines and C++20 in my own projects for longer than that while developing the library. We're already processing billions of RPCs per second in production using coroutines, which I guess is a decent rate, but there's a lot of room to grow in that number because there's only a few distinct code bases using coroutines at Google right now. We're still growing that. Okay, two things to note about Google. Number one, infrastructure needs to handle a lot of traffic, and number two, there are a lot of different people working in the company. Google isn't unique in this respect, but it's extreme compared to a lot of code bases. We'll be coming back to those 2 points throughout the talk. Okay, coroutines and async code are quite general concepts. I've lost my pointer. Sorry. Coroutines and async codes are quite general concepts, and they mean different things to different people. So let's talk about the use case we're talking about here. We're mostly talking about something like an RPC handler that does a fair amount of work that mostly spends its time waiting for other events or RPCs. It's mostly waiting code. It's about efficiently waiting for many things that are happening concurrently in many different requests, not massively parallelizing individual pieces of work so that they can use lots of CPU resources. We're interested more in time than CPU here. We're also probably not at the level of efficiency where we need to optimize out every single heap allocation, which is good because coroutines and C++ have lots of heap allocations. We're doing a little bit of actual work in the RPC handling, so we can tolerate a little bit of overhead for things like setting up and tearing down a coroutine frame, I mean to say. And of course, the reason that that's our target use case is that everything at Google is an RPC, pretty much. Everything is accessed using RPC. It's pretty rare to do any sort of local I/O on a request serving path. It's usually an RPC to some distributed storage system, which internally has RPCs to other systems and other systems, and eventually there's local I/O, but that's not what we're interested in here. So that context is a pretty good one to keep in mind when thinking about the design choices that I'm talking about here. By the way, feel free to interrupt and ask questions. I don't mind. Another thing to mention is that this isn't intended to replace all the C++ that everybody writes all the time. For low traffic code, there's no reason at all you couldn't continue to write blocking code. I think coroutines still have their advantages even for that use case, but it's much less clear, especially in the early days, so set that aside. What we're interested in here is places where there are a lot of concurrent pieces in flight all at once, so it's too expensive to devote a thread to each one. You don't want threads waiting on things. You think of a database or a storage system, for example, that's a good use case. Of course, that's already the situation where we would reach for async code, even before coroutines. It's just that coroutines make the trade-off much easier because writing async code with coroutines can be much less of a pain in the neck than it was before. Okay, now I suckered you into coming to this talk by mentioning the words Google and scale. What do we mean here by scale? You might think we're here to talk about resource efficiency, and that is an important aspect when you're doing billions of RPCs per second, but it's still just early days. We want to be able to deal with lots of traffic. But perhaps more important is scaling in terms of people. As I mentioned, Google has a lot of people. If this library is successful, it might be used by tens of thousands of engineers within Google over its lifetime. And those engineers have various backgrounds. Probably a lot of them will even be new to async programming. And the set of engineers looking at a particular piece of code changes over time as people come and go, and they're maintaining it, they're creating it, they're trying to delete it. So you can't count on any sort of stable expertise. So in general, we want users of the library to fall into pits of success. There shouldn't be traps that make it hard to write correct and efficient code, and instead it should be the opposite. It should be difficult not to do the right thing, like climbing out of a pit of success. Okay, as I said, I'm here to give you a tour of a coroutine library I wrote, focusing on some advanced topics where its design differs from other libraries. But let's start by taking a tour of the basics real quick. Internally, the library is part of a collection of libraries called K3. That name is intentionally silly, short, easy to type, mostly meaningless. It has a silly etymology. I'm mentioning this here mostly because I'm totally going to mess up and call it the K3 library during the talk, so I want you to know what I mean. The first type we need to learn is co. A co-t is the return type for a coroutine that logically produces a t. So co-int produces an int, co-string produces a string. It's purely a marker type. It tells us that this function is a coroutine. So for example, the function declared here is a coroutine that returns a string. The name co is a little strange, but it reflects the fact that this is only a marker type. Like K3, it's just short and sweet. Other async libraries often call this a task or a future. We'll see why we don't call it that here in a little while. So here's a contrived example of a really basic coroutine using the library. We can co-await the result of a function called read remote file to wait for it to give us the data, then resume afterward and print its data. Pretty standard looking coroutine. Before we dive deeper into the technical stuff though, let's go over the basics of how control flow works for a coroutine like that. Take this example where a coroutine calls another one named foo and immediately waits for the result. You're not seeing those notifications here, are you, that I'm getting over here? No. Good, all right. It's not my computer, I'm just making sure. What happens is that when it makes the function called a foo is what's known as a lazy coroutine. So all it does initially is allocate space for the state that it needs to keep while it does its work in the coroutine frame, and then it returns a handle to that space wrapped up in its co-object. It's just a coroutine handle internally. But the caller then immediately co-awaits that object, and that's where the interesting part starts. And I need to figure out the scroll bars on this computer. Okay, here we go. Co-await will suspend the caller and then say, okay, it's now foo's turn to do work. And it will tell foo who should be resumed when foo is done with its work, namely the caller. And then it jumps straight into the start of foo's body. We use what's called symmetric transfer of control to do this, so it really is a jump. It's a tail call with a jump instruction, not a call instruction. So there's no extra stack frame. We'll talk about that a little bit later. And then later, when foo is done with all of its work, it resumes the caller by jumping back into the caller zone trampoline, which knows to jump into the appropriate part of its body, namely the next line after this. That's the basics of symmetric transfer of control. Okay, now with that in mind, let's talk about a design goal of our library. It has to do with parameters accepted by coroutines. We start with an observation that's so obvious you may never have thought about it explicitly. If a function like the one here accepts a reference as a parameter, the reference needs to remain valid until the function returns. Here, the int that the reference binds to can't be destroyed until useInt returns, because there's no way to tell from the outside of this function when it's done using it. If you deallocated it on another thread, that's probably a data race. But what about with a coroutine? This coroutine also accepts a reference to an integer, and it uses it twice. And it probably suspends in the middle while it does something else. When it suspends, it returns control to whomever called it or resumed it. So the answer here can't be as simple as saying useInt must live until the function returns control. It actually depends on how the function is called and how the co-object it returns is used. And I want to be clear about that. I'm talking about returning physical control of the thread here at the first suspension point, because do something may take an hour and then resume on some other thread later. If you return physical control when at the first suspension point, and then you deallocate the int when that happens, it's going to be using a dangling reference when it later resumes. Okay, here's the simplest way that function might be used. It's called, and the object it returns is co-awaited in the very same expression. Full expression, I mean. In this case, the reference will bind to a temporary int, initialized for the function call from the literal 17. But the language's usual rules around temporaries make this work out really well. Crucially, the temporary won't be destroyed until the end of the statement. That's after the co-await expression is evaluated, which means after the function is done doing all of its work. So the temporary isn't destroyed until the function is done using it, which is great. This case is safe. How about this case, though, where you do something more complicated with the return object? Here we call the function to obtain its result object, then we print something in another statement, and only then do we co-await that result object. This case isn't okay. We shot ourselves in the foot. In this example, we hand the temporary to the function, but only co-await the object it returns later in another statement. So the temporary is destroyed before the co-await expression is evaluated. It's probably destroyed before the function is done with its work. With lazy coroutines, this even goes wrong deterministically because lazy start means that the int reference is always dangling before the body even gets the body of useInt async gets a chance to start. Question?
More of a comment. Like I've been doing a couple of these coroutines. I'm finally grokking that sort of concept what you're saying, which is okay. The idea being it's like I know that the variable within the body function is going to be alive. Why do I need to worry about that? And you're like, no, you can't make that assumption anymore just by looking at code. You have to really deeply examine what's going on.
That's correct, although we're going to talk in this talk about how you can make that assumption to give away the ending. In most coroutine libraries, that's right. We'll talk about that in a minute. Yep.
Is that still move significant?
No, it's a single consumer thing. You can pretend it's copyable, whatever. The point is that the temporary is destroyed at the end of the first statement, but you only co-await the thing on the third statement. Anybody else? Yeah.
So within 17, like temporary int, like lifetime extended in the local frame of the coroutine, why would it destroy the temporary int?
It won't be lifetime extended. I don't know the rules of lifetime extension exactly, but it won't be lifetime extended for a function parameter. So maybe somebody can quote chapter and verse here. Maybe that Chandler.
It's a reference parameter. It's a reference parameter, and what you're referring to is lifetime extended till the end of that expression. And that's way too soon.
Yeah, in this case, the temporary is destroyed. I think you mean the lifetime extension where you const int and foo equals call function, and that thing, if that thing returns an int, then it's lifetime extended till the end of the scope. But no, that doesn't happen for function parameters here. Okay, but supporting this kind of usage that we just talked about is common, as far as I can tell. Here's the very first example in the documentation for the CppCoro library. And because of what we just talked about, as in the comment here, you can't tell from the call site whether this is safe or not. It's not safe if the countLines function accepts a reference to a string, because the temporary string will be destroyed before it even starts. Fortunately, in the documentation, it doesn't, obviously. And here's an example from the Folly documentation. They also support this. In this case, it's okay because there's no function parameter, but if you added one, again, it wouldn't be clear whether it was safe or not from looking at the call site. You could only figure it out by looking at other code, perhaps far away in the program, in the code base. But one of the promises of coroutines is being able to make async programming easier. So ideally, almost as easy as writing blocking code. But this issue is a big footgun that we encounter almost as soon as we go to write a function using the usual tools for writing a function in the language. So that's surely going to be a problem if we try to scale to 10,000 engineers with varying levels of experience. So what should we do? Well, the standard is no help. It just warns us, here be undefined behavior. The C++ core guidelines give a really conservative answer. They say you should avoid the problem by not accepting references in the first place. Every coroutine should accept all of its parameters by value. So let's dissect that a little bit. Despite being very conservative, the advice in the core guidelines doesn't even solve the problem, not comprehensively anyway. There are a bunch of possible parameter types that aren't references, but present exactly the same difficulty. So view and span types have exactly the same problem with binding to temporaries. You can accept them by value, but they're reference-like. I don't know if there's a precise term for this, but a string view can bind to a string, and it's just like a reference binding to a string in this respect. You accept it by value, but you're not actually getting a copy. Pointers don't have problems related to temporaries in particular, but they do present the same overall lifetime challenges. Okay, but let's say that we want to amend the core guidelines to forbid the use of these types, despite the fact that it's difficult to even enumerate all of them. Even that's not good enough. Here's a coroutine that doesn't accept a reference, a view, a span, a pointer. Its parameter is accepted by value and copied every time. Is it safe? No, of course not, because the parameter contains reference-like types. A shallow copy isn't good enough. We need a deep copy. We need to say something recursive like never accept a reference, a pointer, a reference-like type, or anything that contains one of those. But even if we say that mouthful of a rule, have we hit all the cases that are important? Well, I don't know, probably not, and it's hard to know. That's sort of the point. The general problem here is that the core guideline is swimming upstream, trying to fight the language. The language wants it to work one way, but the core guideline is fighting it. And that's usually a bad sign. Here are our two functions again. They look nearly identical. The only difference is the return type and the addition of the co-await keyword. This is a strength of coroutines, right? They make async code look like blocking code. That significantly decreases cognitive overhead. So why would we ever want to say that we can't do something like this? Why would we ever want to say we can't write code like this? Saying that coroutines shouldn't use the same language features as all other functions, especially for something as basic as a function parameter, it seems to be throwing away one of the biggest advantages of coroutines. If you can't tell, I don't think that the core guideline has thought this through terribly well, certainly not thoroughly. Anyway, my point is this will be a people scaling problem. We have to teach people to use different basic rules for different types of functions. It's for something as obvious as a function parameter, and I think we should avoid that. Okay, I can't resist though. Here's one more important case the core guideline doesn't handle. A this pointer is an awful lot like a reference argument, and it has the same issues discussed in the guideline. But should objects really not be allowed to have async methods that otherwise work just like normal blocking methods? I mean, you simply can't write an async method according to the core guidelines if you take the spirit of it. That's another big usability problem for coroutines. So again, I don't think that guideline is reasonable. And of course, saying just avoid references is also a problem for resource efficiency for that sort of scaling. It forces us to copy every parameter to every coroutine. Those parameters may be large. And remember, we need a deep copy. And yes, we avoid the copy of the parameter itself if we hand it over as a shared pointer. But then we're forcing an out-of-line heap allocation, which is also can also be an efficiency problem. And it's also worth noting that not every object is copyable or even movable. And also out reference parameters have their place now and then too. So sometimes it really is desirable to use references. All right, it's clear I think the core guideline is naive and harmful to performance, so I'll stop harping on that. For my library, I chose the following rule. Unless documented otherwise, every coroutine requires that its parameters are usable until it's done with its work, either because it finishes or is stopped early. This is like an implicit requirement of every function that returns co, unless documented otherwise. So that's references, everything like a reference, including this pointers and view types. You must not destroy an object while its method is still logically running. That's the this pointers. Now, I'll pause to note that this is an obvious set of rules because it's exactly the same set of rules we have for all functions, right? We've just generalized from until the function returns to until the function is done. And I think that's a really natural generalization. Do you have a question? No?
No.
Okay, just making sure.
It's an easy statement to make. How can you enforce it?
Yes, thank you. Next slide. Okay, so now we're back to where we started with the problem of easily getting dangling references by accident. We've just said that's illegal, so what can we do instead? Now remember, we're considering two sorts of callers here. We've got caller A, who immediately awaits for the result of the coroutine, and caller B does something fancier, delaying awaiting until later. But importantly, most call sites look like A here. It's significantly less common to need the shape of code in B. You often see it, but don't actually need it. And it's even like often a code smell. It'll be cleaner if you express it in one expression. So I would also argue that B is a much less natural code site. For example, it's impossible to write B with normal functions. There's no way to like start a function, do something else, and then join it, right? Except with spawning a thread. With normal functions, you simply can't do this. So we have less intuition about how it should work in the language. So we can say it's less structured in a sense that I'll talk about later. So our answer here is really simple. We just ban form B. You're not even allowed to do this in the K3 coroutine library. It won't even compile. If you're curious why doesn't it compile, here's some advanced C++ nerdery that this room will probably mostly understand. The way we ensure that caller B doesn't compile is by making co non-movable. and we accept it by value in the co-await implementation in the promise type. So it means the only way to await it is if you do so immediately in the same full expression as the function call, so that guaranteed copy elision can kick in. And again, because contemporaries aren't destroyed until the end of the full expression, that means that lifetimes work out perfectly using the usual language rules around lifetimes, just like with blocking functions. Yeah, question?
So it's still common to maybe want to spawn several tasks.
The question was, how do you spawn several tasks? We'll get to that as well. Yeah, you get the same benefit of the same usual rules around lifetimes of temporaries, just like blocking functions, and we're no longer swimming upstream against what the language wants us to do. Of course, this is C++. You can still shoot yourself in the foot if you try, but it tends to be in similar ways that you can do it with blocking functions. It doesn't happen by accident anymore with a innocent-looking call site, and we get full support for references and reference-like types. Okay, you may have noticed a sleight of hand. I eliminated the problem with references by just declaring an entire pattern of code illegal, but that pattern is useful sometimes. What if you really do want to call the coroutine separately from awaiting its result? No problem. The answer is that we have a separate class for that case called future. If you want to obtain a future for the result of a coroutine but not await it in the same full expression, use this class. Notice that the code looks almost the same as call site B before, but just with a constructor call instead of a direct function call. The future class takes care of making this safe by ensuring that everything is copied. It's exactly what the coroutine, what the core guideline says to do, but on an opt-in basis and without the coroutine itself needing to cooperate. It copies the constructor parameters in the same way that std bind front does, in the same way that the std thread constructor does.
Std async.
It is still lazy, yes.
No, like std async.
Oh, std async maybe does the same. I'm not familiar with that one so much. Yep.
Yeah, so you might have already answered it, but why do you need to provide the function and the arguments separately instead of just providing the call as an expression?
Oh, sorry, have I highlighted something over here? The question was, why do you need to provide the function pointer separately from the arguments instead of a call expression? It's the same reason as before. The call expression the temporaries that are part of the call expression will be destroyed as soon as this statement finishes. So they need to be separate. And the future constructor takes care of copying them, of interning them, the same way that bind front does, for example. And I want to observe, I think this matches intuitions in a nice way. C++ programmers are accustomed to references just working. I'll get to questions in a moment at the end of the slide, sorry. C++ programmers are accustomed to references just working with temporaries and in function call expressions, but they're also accustomed to the issue around references in constructors being a little bit more nuanced. So basically, this is like half the responsibility of the task or future types in other libraries, with co being the other half. But splitting them into two separate APIs makes for the usability and efficiency win in the common case of caller A, where you immediately co-await. And by the way, this is why we gave the return type the name co, which is sort of meaningless. It's nothing but a syntactic keyword that the marker for this is a coroutine, like an async keyword in another language. If you want a future for the result, that's a separate class. Okay, questions? Yes.
So just to be clear, in this code, the parameter is not binding to that 17.
It's not binding to that 17, correct.
To an internal copy of the 17 that is stored by the future.
Yeah, in this code, the future internally has a type this is a type erased implementation where internally there is a copy of 17 that the parameter binds to, and it takes care of the lifetimes working out, just kind of like bind front. Yes?
And do you do that by essentially creating like a trampoline coroutine that takes everything for value?
The question was, do you use a trampoline coroutine? The answer is yes, unless there's some optimizations, but the general form is internally there's a coroutine that accepts everything by value. So it's copied into its own coroutine frame, and then its body is just co-return, co-await, call expression, and it all works out. So it also handles implicit conversions, which I haven't talked about here.
Okay.
And
Yes.
then the run function, the move is necessary to make sure that you've consumed it for life.
Yeah, the question is, why is there a std move here? The answer is just, it's what is it, linear type? That you can only consume it once, so this marks it in the type system.
And also then run only acts on our value, so that
Yeah, run is R value ref qualified, yes.
What happens if you destroy the future without calling its run method?
Question was, what happens, I'm repeating the questions for the microphone. The question was, what happens if you destroy the future without running it? The answer is everything works out. The body of the coroutine never starts. Everything's deallocated as appropriate. Okay, I'll move on. Here are some more realistic examples of when you'd use a feature. Typically, it's not because you want to stick in an intervening print statement, that's just an example for a slide, but because you want to call a concurrency API. So here are two functions that accept features as input and add concurrency in some fashion. Fan out runs them all concurrently, race runs them all, fan out runs them all concurrently and waits for them all to finish. Race does the same, except it finishes as soon as one of them finishes. Just two examples. Okay, let's shift gears to another topic. Another scale thing about Google is that our fleet has a ton of active threads at any time across all the machines and all the programs. So as a result, we spend a lot of memory on thread stacks. And to avoid that being too expensive, we run with thread stack sizes that are rather small. 64 kilobytes is common. And I'll poll the room, is that small in your environments? I got some head nods, yeah.
Efficiently big.
Say what?
16K.
16K, good, even smaller. There are some 16K stacks at Google, I believe, but yeah. Anyway, I think the default on Linux is 2 megs, something like that? Yeah, okay. Anyway, this is part of an interesting feedback loop where we spent a lot of engineering time pushing the feasibility of a thread per request model as far as we could get it in one corner of the design space. If you've seen talks about Google Fibers, which are not what everybody else calls fibers, you know what I'm talking about. But on the one hand, that gave some really useful results, but on the other hand, it simply can't be pushed far enough for some applications where you have many concurrent pieces of work. That could be its own talk, though. Question? No? Okay, sorry. So, of course, smaller thread stack sizes makes it more likely to have stack overflows. And the real problematic part about stack overflows is there's no authority in charge of who gets to use what amount of stack space, and it's hard to know how much is appropriate. If you're one programmer, you control the entire program, you can do this very carefully, but if you've got 10,000 engineers, each writing libraries that call other libraries, it's much harder to do. Because a library with a deep call stack might work totally fine normally, but it'll be the straw that broke the camel's back when it's used in another context where there's less stack overhead available because there's more stack used underneath it. And this can be particularly problematic for async code, since async loops usually involve unbounded recursion, especially if unexpectedly things are immediately ready. So unless you bounce off of some sort of event loop with each iteration, it's really easy to get a stack overflow. And of course, debugging stack overflows is a real pain. It often takes me a fair amount of time just to realize that the segfault I'm looking at is a stack overflow. And I've debugged stack overflows way too many times. So if it happens to me, a new engineer with no experience in this is really in for it. So we see that stack overflows are an efficiency problem for thread memory, but also an expertise scaling problem. Question?
Yeah, I think Rust uses some sort of guard pages to get a message from a stack overflow. Can't you use a similar technique? Or? The
question was, can I use guard pages like Rust to find stack overflows? Yeah, there's lots of techniques around stacks. I don't know, does Rust have segmented stacks and they grow on? No.
No. Just
okay, to get better debugging. Yes, Google actually has. I believe we actually do use this technique. It shows up in the crash dump, but it's like one tiny line you got 1,000 threads. It's in the middle of yeah. We actually should have better tools around this. I take your points. But still, I think a new engineer may not even know what that means. Yeah. Do you know what I mean? And much less what to do about it, especially if it's in some library because the binary owner is the one that gets the crash dump, and the library owner is the one that chooses how much stack space to use, Okay, but coroutines give us an opportunity to improve this situation. As we talked about before, the API for suspending and resuming in the language, the low-level API, has a mechanism called symmetric transfer of control. It allows us to hand off control to another coroutine without using another stack frame. We talked about this earlier on the control flow slide. So if you remember, it guarantees a tail call into the other coroutine, and then you can do it again on the way back out when the coroutine finishes. There's no need to have a stack frame to return to because everything is a jump instruction, not a call instruction. And I think this is actually the only guaranteed tail call in the standard. It's actually kind of like a unique mixing of levels of abstraction. Please correct me if anybody knows otherwise.
It's also broken, or at least it was broken in certain versions of compilers.
Yeah, yes, definitely implementations have had trouble with this. I've filed many bugs inside Google, and all of them have been fixed. As far as I'm aware, Clang does a pretty decent job of this at main on the main branch.
So GCC 10 definitely has Stack Overflow for long chains of semantic
Okay.
answers.
You say the comment was GCC definitely has Stack Overflow sometimes. Yes, but that is a GCC bug according to the standard.
Of course.
If you like standard ease, here's how they guarantee tail calls in the standard. I guess they don't actually call it a tail call. Instead, they say you can hand off control any number of times, but it amounts to the same thing because I can't see a way to implement that guarantee with a normal function call. Oh, I went too far. Okay, so that works out really nicely when there's a traditional caller and callee relationship between the two coroutines. They can just hand off control back and forth. But what about when there's a less direct relationship between them? Take an event API like this. It lets one coroutine go to sleep and another wake it later when it decides the first should run again when some application-specific condition is met. So how should this work? In particular, how should notify work? The reason this is more complicated than the caller and callee relationship is that here there's more than one coroutine that wants to run at the same time. When calling and returning, only one wants to run at a time. The caller suspends until the callee is done, and then that's exactly when the callee is ready to hand control back to the caller. So there's only one at a time. But say we've got these two coroutines. The first one suspends to wait for the event, and then the second comes along and notifies it. But now both of them want to run. The notifier wants to continue on and do whatever it was going to do after it called notify, and the waiter now wants to wake up and continue with its own body after the wait call. So we've got two pieces of work that are runnable, but the thread that ran the notify method is only one thread. It can't run two things at once. So what do? Probably the most obvious choice is to resume the waiter inline directly in the notify method. It would parasitically do its work on the thread that called notify. It would run inline and prevent notify from returning until it next suspends and releases control back to notify because it doesn't have anything else to resume. That's exactly what the event type does in CppCoro, for example. And internally in Google, we've got other stuff like this. But the problem with that is that it violates our design goal. Because if a coroutine calls notify on some other event, if a coroutine calls notify, that means that the waiting coroutine will resume inline from within that coroutine, and we'll have to spend a stack frame on that. There's a stack frame for notify. But if that coroutine calls notify on some other event, then it may resume another coroutine inline, which will cost us another stack frame. And we might continue in this respect indefinitely, and eventually we'll get a stack overflow. So it would be nice to avoid this. Now, the only way I can see to provably avoid ever having this problem is to take an extreme position. We make another design choice here. We're never allowed to have one coroutine directly resume another. It means that we can never have a situation where we get stack frame buildup due to coroutines waking other coroutines. There is only ever at most one stack frame per thread devoted to running a coroutine. So we've truly bounded our stack usage for coroutines. But yeah, again, we still haven't answered the question about the event class. How should the notify method work under this rule? Okay, well, we have two things that we want to run, and there's only one thread to run them on. So we could resolve this by breaking that second part and the assumption that there's only one thread available. Instead, we can resume the coroutine on a different thread and let it run concurrently with at the same time as the notifier. Maybe I should say in parallel with the notifier. That's sort of what you would get if you implemented event for a blocking ecosystem in terms of mutex and a condition variable or something like that. But at the same time, it's not, because in that ecosystem, you already have threads to block and wake. You're not introducing a new thread through the event API. There was already the notifying thread, and there was already the waiting thread. With coroutines, the whole point is that we don't devote a thread to waiting on anything, at least in this use case. So the question is, which thread should we resume on? Remember that we have only one thread in scope, let's say. It's the one that called notify, and we haven't mentioned any other threads, so there's not really a thread to use. Since we only have one thread in the picture, we need to somehow use that thread. We make another design choice, and that's that the core coroutine library never adds parallelism. They never introduce new threads into the picture. Wherever the thing a coroutine is waiting on finishes, that's exactly where it will resume in terms of threads. And that means that the user doesn't need to worry about understanding why extra threads suddenly come into the picture, and it also tends to be pretty friendly to CPU caches. For example, if you're waiting on an RPC to finish, you're going to wake up on an RPC reply thread, a thread reading replies from the network, and all the data it just read is already going to be in the CPU cache. Yes?
What is meant by ready to resume? Is that not the same as the first call to the coroutine?
The question is, what is meant by ready to resume? It depends on what you're waiting for. If you're waiting for an async sleep function, sleep 2 seconds, it's probably going to finish on a thread that has a heap of timers to deal with, for example. If you're waiting for an RPC to finish, it's going to wake on some sort of network thread that's reading replies from the network. If you're waiting for, I have a sparsity of examples here because we always wait for RPCs at Google, right? But the point is, whatever thread notices that the thing you're waiting for has finished, that's where the coroutine will resume. By default anyway. We'll talk about how you can modify that. Okay, so we have two things, and we've decided they must both continue running on one thread. They can't both run at the same time on one thread, so they have to take turns somehow. The way we do this is by scheduling the resume coroutine to run sometime after the notifying coroutine next suspends. We arrange it so that coroutines always run in the scope of a loop that's resuming work from a thread local queue. When that work finishes, it returns control to the loop, which resumes the next piece, and so on until it runs out of scheduled work, and then it releases control. So notify schedules into that queue. And again, this is a thread local queue. Yes?
So potentially, if you still wanted to resume the other coroutine, you had to, and not take up more stack space, you need to suspend the caller of notify. Could you have made notify a co-void function and co-await notify?
The question was, could you have made notify itself a coroutine, so it's co-void, and it can suspend while the thing that's being notified resumes, and then later it will resume when it's done doing its work? Yes, you could. In fact, that's how I originally designed this, but it turns out being able to call notify from non-coroutines is also extremely useful. It's a generic mechanism to wake a coroutine from absolutely anywhere. And in that case, it actually does go inline, and it does all the coroutine work, including all that thread local queue processing and so on, and then it releases control. So you don't really want notify to be a coroutine so that you can call it from outside. At one point I had both, but if you think about it, having to call co-await notify, so you could suspend while the other thing does its work, it's not so different from what I came up with here, which is when you next suspend, it will do its work. It's just a question of who goes first and who goes second. And there's one definite advantage to this way that I'm going to talk about in just a moment. On this slide, in fact. So it's worth pointing out a nice property that we get for free here because we don't resume the coroutine in line. That is that it's okay to notify an event with a lock held, even if the coroutine that you resume immediately takes the lock as its next action. You won't deadlock. Because you will release the mutex by the time it runs. So this turns out to be surprisingly convenient. It makes it really easy to write coroutines that wait for things to happen with lock-guarded state, especially like internally to a class, preserving invariance, that kind of thing. Now, a lot of other async libraries have a notion of an executor or an event loop. I think it has some other names too. They might solve the problem of where to resume the waiting coroutine by saying we schedule it on the executor and the executor deals with the problem. I've chosen not to incorporate the notion of an executor into the core K3 library here. So let's talk about why. The reason is basically that we don't need it. We can get what we want without offering the user any sort of knob, configuration knob. And fewer knobs is usually better, in my opinion. The library is totally agnostic to executors. It doesn't know anything about them. All it has is its one thread local queue of things that have been resumed by the running coroutine on that thread. Now, of course, individual things you wait for might have an executor internally. Like if you're waiting for, as I was saying before, if you wait for an RPC to finish, you'll probably be resumed on one of a team of threads that are reading RPC replies from the network. But the core coroutine library doesn't know about this, and it doesn't need to. And of course, because the general rule is that coroutines resume where they become ready, the user can bounce off an executor and switch threads if they want to. All they have to do is explicitly await something that becomes ready by scheduling it to do so on the executor of their choice. So there's no power lost here. We just don't do it by default. And I think that's a better default. Executors are really common in other Google async APIs, and they're kind of a nightmare. We always seem to wind up in a case where each code base uses its own custom executor, and it might once have been for a good reason and carefully tuned, but has long since turned into a haunted graveyard that nobody understands exactly why it does it that way, and everybody's afraid to change it. So I think it's better to encourage things to happen naturally where they become ready to happen, and than it is to mess around with thread pool mess around with thread pools at each API boundary. It's better to do it at the edges of the system, like incoming RPCs and that kind of thing. Now, I don't know if this happens elsewhere, but at Google, someone came up with a clever idea of an inline executor that runs scheduled work immediately inline in the schedule method. And that sounds really clever at first. You can use this to like hack the executor interface to have the behavior that we just talked about. But it's too late by the time that you realize that it completely breaks the guarantees of your programming model. The point of always bouncing off an executor is that nothing happens in line. You can notify events under a lock, you don't get stack frame buildup, and so on. But then once you abstract away the notion of an executor and let users configure it, you get implementations where none of that is true. And suddenly you do get stack frame buildup and you do get deadlocks and so on. At Google, it's really common for code that accepts an executor to simply fail to work correctly if the caller provides an inline executor, even though that's something the API totally allows them to do, and inline executors are rather widely used. You just forgot to test it. But the K3 coroutine library can't have that problem because it doesn't let users inject the executor. Okay, let's move on to another topic, which is cancellation. This one's near and dear to my heart. I think this is sometimes an afterthought in library design. You bolt on cancellation. You bolt on a cancellation token type that you can choose to accept in your APIs or not, and you add cancellation support to some but not all awaitables, and you call it a day. Now I've got cancellation. But I think cancellation is really important. It's very fundamental to distributed computing. I saw some thumbs up. Good. Yes, I agree. You're my people. You can't do request hedging without cancellation, for example. That's send one request, wait a while, send another, and race the two, for example. You don't want to waste work on doomed requests that you know you don't need the result for. And what are timeouts but just time-based cancellation? All of these things are really important for avoiding wasted work and unnecessary waiting for the end user. But the thing about cancellation, in my experience, is that people also frequently get it wrong. It's very common, at least inside Google, to write code that belongs to some ecosystem that supports cancellation, but not actually support it in your function. Your function is just oblivious to it. You didn't register the appropriate callback or whatever. And the insidious thing is that this mostly appears to work until one day it doesn't, and you've got mysterious latency or deadlock problems because it turns out cancellation just didn't work. And you'll see this in prod when you get your 99.99th percentile request, which happens all the time when you're doing billions of RPCs. So we want users to fall into a pit of success where, with respect to cancellation, where if they want to ignore it, they can, but they have to explicitly work to do so. The default should be that cancellation just works. So here's my design choice. The caller of a coroutine is always in control. If the caller no longer wants the callee to run, the callee should stop running, and it should do so promptly. Not after getting a response to some RPC, not after a timeout expires, immediately. All it should get to do is the kind of thing you want to do before you release a lock or unwind after an exception. You need to ensure that internal variants are restored, that kind of thing. No waiting for stuff. So we make cancellation impossible to accidentally ignore by making it non-advisory. When a coroutine is canceled, it simply doesn't resume the next time it's suspended. Of course, destructors still run. In this example, we do an async sleep for 2 seconds. If we're canceled before then, we print a message in a destructor. That's the absel cleanup API, which is just a anonymous destructor type. But otherwise, we disable the destructor. That's the .cancel, which is kind of confusing in this example, I know. But note that there's no cancellation token to worry about plumbing through. We don't have to accept a cancellation token type. We don't have to remember to register a callback with it, nothing like that. If you're canceled, you simply never wake up. You have no control over this. All you get to do is run destructors. It's as if an exception were thrown by whatever you're awaiting. Oh, questions, yes. Sorry, who was, yes?
K3 sleep isn't aware of the cancellation.
The question was, is co-await K3 sleep aware of the cancellation? The answer is yes. In order to write awaitable types, you do get something like a cancellation token when you exit the ecosystem, and you do have to do things like register callbacks. So the thing about you don't resume, it's implemented that way with callbacks underneath, but you don't see it anywhere in the coroutines themselves. You only see it when you exit the ecosystem through some sort of bridge.
And so my comment was, okay, so if your coroutine stops early, you won't wake up from suspend. Great. But the destructor will still run. How?
The question was, how do destructors still run? The answer is magic implementation details that I can tell you about later when I remember them, if you want to hear the details.
Oh.
I mean, mean, when Destructor coroutine frame is destroyed, so do all local variables.
Okay,
And
yeah.
as complaint of push leap is merely a local variable, it gets destructed.
That's a better answer. The language itself helps with this. It's stood coroutine handle has a destroy method, which knows from the internal state machine that the compiler generates which destructors to run when you call it based on where you were suspended.
Right.
The question of how destroy gets called that's the magic implementation details, but maybe not what you were asking.
Yes, thank you.
Okay, I'll move on. So let's talk now about concurrency APIs. By that, I mean APIs that let you turn one coroutine into multiple. This sounds like a change of subject, but I'll eventually tie it into cancellation, I promise. So one way we can write a very general concurrency API is with a fork and join model. Whenever you want to start another coroutine, you create, here I call it eager future. It's not a super great name, but whenever you want to start another coroutine, you create an eager future object, which starts running it as soon as possible after cancellation. But of course, because we never have one coroutine running on top of another on one thread, that's never sooner than the caller's next suspension, just like the notify method with event. The eager future then runs independently until you later join it with a join method, which obtains its result. Now, another route you can go is to prefer what's called, it's often called structured concurrency. I learned this term from a really good blog post by Nathaniel J. Smith called Notes on Structured Concurrency. I recommend it. The general idea is something like children never outlive parents. Eager future isn't structured because it's movable. The function that creates it can hand it off to other functions or even return it, for example. The new coroutine may outlive the one that created it. But compare that to fanout here, which doesn't allow this. It lets you get n concurrent threads of control in form of coroutines, but they're all peers. They're siblings, and the parent can't move on until they're all done. Now, one reason to prefer structured concurrency is that it tends to make code safer. In fact, this is probably the primary reason. In particular, it's pretty hard to get object lifetimes wrong when you never proceed until the concurrent work is finished. It's just like what we talked about earlier with the natural parameter lifetimes. You can freely hand over references to local variables that are owned by the parent coroutine, as in this example. And since the parent never goes on until the child is finished, you know that they won't be destroyed until the child is done with them. It's very much like a function call. So this is a boon for people safety, but it also helps with efficiency. Natural lifetimes for objects means that you don't have to play games with copying values all over the place, or heap allocations for shared pointers, or reference counting for shared pointers, or anything like that. It's all just raw references that work out safely automatically. In contrast, it's pretty easy to get dangling references with unstructured concurrency. The general problem is that the language's lexical scopes, the curly braces, they don't align with what I'm going to invent a term here, concurrency scopes, the lifetime of this coroutine. In this example, the bug is pretty obvious, of course, but it can be easy to miss in a really long function with a bunch of other stuff going on and branches and optionals and that kind of thing. Another nice thing about structured concurrency is that it's obvious how cancellation should work. If the parent is canceled while the children do their thing, well, the parent was awaiting those children, so clearly we should cancel the children too. Because the lexical scope matches the concurrency scope, cleanup also works in an obvious way. You join the children, it will cancel and stop the children, and then run the destructors in the parent, and then so on up the stack. All of the destructors run in the children first, and then in the parent. Now you might wonder how propagating cancellation from parent to child works in what I just said. In particular, how could we do it without violating our goal of bounded stack usage? What if there's a really long parent-child chain to clean up? That's a problem because destructors love to use stack frames. But the answer, of course, is coroutines. There's actually another lower level coroutine result type in my library called loco, and it itself does not support cancellation or async code. It doesn't support waiting for things that happen later. We use it as sort of a strength reduction thing to implement the cancellation path, which lets us use symmetric transfer of control because we're co-awaiting the child cleaning up its stuff. So the child can do all of its cleanup work while the parent waits without the parent needing to devote a stack frame to waiting, which I think is kind of cool. Question?
So fanout takes a vector of futures or whatever, and futures are constructed with the function pointer and separate arguments in order to avoid the lifetime problems. But fanout doesn't have lifetime problems because it uses structured concurrency. Do you have any thoughts about
The question was,
Is that extra ceremony onerous in practice? And if so, do you have any thoughts about how it can be avoided?
it's a great question. I'll restate the question. I think I got it right. We introduced future by saying it's used to avoid reference lifetime problems, but fanout takes a vector of futures. Fanout itself doesn't have reference lifetime problems because it's structured concurrency, as I just said. So what's with, like, is that extra ceremony onerous? The answer is, a couple weeks ago, I realized, yeah, you're exactly right. And there is an overload of fanout that takes essentially a vector of co-objects, but dealing with the non-movability to make that work so that it's a little bit more convenient to call, less onerous, and less copying as well. But in the general case, you can't do that because if you want to make that usability optimization, let's say, you need to have the set of call expressions to be fixed at compile time because you need the call to fanout to be in the same full expression as the call to all the children. So it's a fixed number of children. But in the general case, you may have an arbitrary runtime number of children. So you still need the vector future version. Does that all make sense? Okay, yes?
You do the cancellation in a loop and you co-wait for each cancellation to take place, right? That means the cancellation happens sequentially?
Yeah.
You fully wait until the first child to cancel
Yeah.
before you... I mean, I thought, thinking about parallelizing this thing.
Yeah. The question was, since we co-wait in a loop here, the co-wait is the cancellation is sequential. One child's destructor is all finished before another. I don't think that there's any guarantee about the order. In fact, I think I randomize it internally. But could you parallelize it? Yes, I guess, but it's not really the goal of the library, especially because, again, they don't get to actually wait for anything. They only get to run destructors. So it's expected they should be quick. It's not like we need to do them in parallel for latency or anything like that. It could be a latency problem in extreme cases, absolutely, but for this simple interface, we haven't done that.
So just to be clear, this pattern is predicated on the assumption that destructors are always quick.
The question was, this pattern is predicated on the assumption that destructors are quick. Yes, that's sort of an implicit rule here. If you read the ground rules for the library, one of them is you never spend too long occupying the CPU. Again, you're mostly waiting for things. You could write a destructor that waits for an RPC to finish and shoot yourself in the foot in terms of blocking an RPC thread that needs to go on to deal with the next reply or something. But that was also always true. It's just you have to work explicitly to do it. And there's some co-evolution here with the Google style guide, which I feel this is not a super well understood topic within Google, but the general spirit is destructors should be quick. Yes, they shouldn't be waiting on RPCs to finish external events, like that kind of thing. Okay. All right, I guess it's also clear how cancellation should work for the unstructured type, eager future. We're in a language with destructors, so we should use them, right? The destructor should stop the associated coroutine before it returns. Of course, it needs to do all of the cleanup before it finishes, which means running the destructors in the canceled coroutine as well. But whoops, we've gone and created a Stack Overflow for ourselves. Here's a kind of annoying example. The function foo creates a chain of n coroutines with each link controlled by an eager future object. And the function bang calls foo with an argument of 1 million. It waits a moment for it to set everything up, and then it cancels it. This will cause at least 1 million stack frames, one for each eager future destructor, as they clean up after each other. So we violated our goal to have bounded stack usage. Nope. You might have been thinking I would switch to the next slide and it would say what I did to fix this problem, but unfortunately, no, I don't have a general fix for this. The problem is with the language. Destructors can't be coroutines, so there's no way to use symmetric transfer of control to repair this problem by transferring control between destructor coroutines. If you're going to use destructors to have cancellation, to do cancellation, you're going to have a stack frame per coroutine in the chain, at least in the worst case, unless you do something silly like spin up a thread for each coroutine to run its destructors. Destructors love to use stack frames. That's the problem. Okay, I tricked you a little bit. I do actually have a really over-engineered solution to some of this, but it's a royal pain, so I'll just summarize it here. We teach the coroutine promise type to understand a special parameter type called async cleanup. When it sees that as the first parameter in the coroutine, it records a cleanup coroutine that it can call to destroy the interesting state for that coroutine. The eager future destructor in turn, it knows to call this function to do stack-friendly cleanup if it's present. So the first eager future destructor call will clear the way for all the rest of them. It will use symmetric transfer of control to do all of the cleanup, and then the later ones don't actually need to do anything. But this is super ugly, and it's only worth it in like specific situations where you expect really long chains of coroutines. Like if you want to implement functional programming techniques that basically only work in Haskell because it has guaranteed tail recursion, that kind of thing. Yes?
This pattern feels very similar to another problem. How do you handle failure, cleanup failure? Or do you pretend it doesn't exist?
The question was, how do you handle cleanup failure? The answer is destructors don't get to be coroutines. There's nothing you can do about it. Destructors don't get to return values. There's nothing you can do about it. This is a problem with the language, right? If you need to do that, you need a different type of cancellation. And this is actually often an objection I've gotten from people inside Google. It's like, well, I do want to support cancellation, but I need to flush this buffer, or I need to like send an RPC to another system when I'm canceled to tell it I've been canceled. The answer is, you can totally do that, but you're just on your own, right? In that case, you will need some sort of cancellation token type that has its own semantics about, you're not really canceled, you just should return soon or something. You can model weaker forms of cancellation, but it's up to you to do so. The one that's built in is, sorry, you're done running, and you only get to run destructors.
So for the K3 library we're discussing right now, no cancellation, no cleanup failures.
Yeah, I guess the way I would say it is, we offer one primitive for cancellation, and that is you stop just running destructors. If you want to do something else, totally, like you can write whatever code you want to write, and it would look something like, you know, an atomic bool that's something like cancellation token and a stood cancellation token that says, I really wish you would clean up soon, but feel free to do so gracefully. And you can do whatever you want with that, including retry cleanup failures and that kind of thing. But if it's, I want you to stop now, that's the semantics that we give you in the core library. You have no choice over that because you were brought into this world by your caller, and you can be taken out of this world by your caller. Does that make sense? Yep.
Is it possible for a coroutine to gain access to an eager future that represents it and request its own cancellation while still in CPU?
Can you say that again? Sorry.
No. Could it be possible for a coroutine to somehow, like I know, through sort of a deliberately based like captures and whatnot, to gain access to the eager future object that represents it, and zero it out to request its own cancellation was still not suspended?
The question is, can a coroutine that's controlled by an eager future somehow gain a reference to that eager future and cancel itself?
Yes.
Sure. The language will let you do that if you play games with like, it waits for an event that says, I've now stored a pointer to your eager future, and then you notify that event as soon as the eager future is created or something like that. It could indeed do that, and let me think about what would happen if it destroyed the eager future. I believe it would all actually work out. It would continue running until its next suspension, and then it would stop running. No, that can't be right because the destructor waits. Yeah, you get a deadlock. Don't do that.
So the answer is don't do this.
Yeah, and that's common though, right? I mentioned Google Fibers. It's a bad name. Please don't take the implications of the word fiber. But the fiber destructor, no, that's not true. The fiber destructor has a requirement that you join the fiber before you destroy it. But if you join yourself, you're going to deadlock. It's the standard fork join problem about if you join yourself, you're going to deadlock. Avoid unstructured concurrency, right? Next question.
You said stood cancellation token, you mean stop token?
Oh, sorry, I forgot what it was called. Yeah, I think I meant stop token, not stood cancellation token. Is that what it's called? Sorry about that. Other APIs often call it a cancellation token. I meant stop token, yes. Okay. Okay, all of that is really annoying, and it has runtime overheads too, right? So I just want to say, like, Rust is working on asynchronous destructors. I think it's an experimental feature at least. Is that right? I don't know. I don't know Rust super well. But why can't we have asynchronous destructors, right? I don't think it's totally crazy. There would be so much to think about. Maybe you don't even want to call it a destructor, right? But some sort of async RAII. I know there was a proposal for this, P1662, but as far as I'm aware, it never went anywhere.
Correct.
I just want to pitch that. It would be useful to avoid this kind of problem, and the others that I've mentioned throughout the talk. Okay, but to be clear, until we do have async destructors, we can also just not use unstructured concurrency. We want to use structured concurrency wherever possible, because it totally avoids all of the problems I just mentioned. Here's another one of those problems with unstructured concurrency. Let's say that we have a thread pool that's used for making RPCs. It's got exactly n threads, and each one is reading replies from the network. When an RPC finishes, the application is told on one of those threads, okay, the RPC is done now. And furthermore, let's say that the RPC framework, it deals with cancellation by scheduling work on that thread pool to tell the application that the RPC failed. This is exactly how Google's Stubby and gRPC work. Here, foo uses an eager future to make an RPC. But if foo itself is canceled, then the eager future destructor will block on canceling that RPC and cleaning up after it, which requires scheduling work on the thread pool to be told, yes, I'm done cleaning up. But foo itself may be running on one of those n threads. So we've got one thread in the thread pool waiting on another piece of work in the thread pool. And if there are n copies of foo that all happen to be canceled at the same time, we get what's called a thread starvation deadlock, where nothing can make progress because one of those things need to finish before the others can make progress, but they're all waiting, occupying all those threads. What's the moral of the story here? We could give up on destructors for cancellation to avoid issues with stack overflow and bounded parallelism that I just mentioned, but then you lose all the benefits of RAII. It would make the unstructured API a lot harder to use reliably, which is a people scaling problem. So I think the current trade-off is decent. If anything, the moral of the story here is avoid unstructured concurrency wherever possible. But that's not to say you should never use unstructured concurrency. I initially tried to take a hard line on this by having only structured concurrency APIs, but it's just not realistic. Sometimes the nature of something really is unstructured in the sense I've defined. So a good motivating example for this is when you want a coroutine as a class member that's doing some background work, some async background work for as long as the class object exists. And that's really fundamentally unstructured, and you really do want destructors to do the right thing here. Okay, so let's recap and see how we did with our scaling concerns and design goals. Our first design goal was that natural parameter lifetimes for coroutines should always work, lifetime rules for coroutines should work in a natural way. I think we did pretty well here. We say that the rule that everybody needs to follow is exactly that, natural parameter lifetimes. And it completely alleviates any burden for an author writing a function. They get to just use references freely, no problem. For callers of a function, this also works decently well, I think. In the normal case where you immediately co-await the result, everything just works out thanks to the language's usual rules. For the case where you need to await later, you have to use the future class instead, but that's not so difficult. It has safety comparable to stood bindfront and stood thread and stood async, it sounds like. And it's got the same semantic as those APIs for what gets copied, namely a shallow copy. The next design goal was bounded stack usage. The main point there is to fit in with Google's unusually small thread stacks, but I don't think it's Google specific. Bounding our stack usage also means that we can do useful things like unbounded recursion, regardless of the environment in which we're running, because you will hit your thread stack sizes eventually if you do unbounded recursion, without this library anyway. So again, we made a design choice that makes this all work out, at least mostly. We said that one coroutine can never run on top of another on a single thread, which means you'll never get a stack overflow in the happy path. You also never get one in the cancellation path if you use structured concurrency, but the picture gets a little bit more complicated with unstructured concurrency. But unfortunately, I think the language forces that on us. Now, as a side effect of our design choice here, we also get a bonus pit of success, and that is that the coroutine starting and waking APIs can never cause a deadlock due to holding a lock. And with cancellation, we made the design choice that the callee has no say in the matter. They don't get to choose to just keep going while ignoring cancellation. They can run destructors, but otherwise they have no say in the matter. And that means we have the pit of success where it's impossible just to not know that cancellation needs to be dealt with. You have to use RAII, and beyond that, everything mostly just works. I'll conclude with some lessons to keep in mind, trying to generalize what we talked about here. The first is that thoughtful API design can be an efficiency win. With some thought about how the coroutine return type should work, we gain the ability to use references without it being a big safety problem, which reduces copying. And with a focus on structured concurrency, we get the same thing, less copying, more efficiency in concurrency APIs. And the same goes for bounded stack usage, saving memory, and better guarantees about cancellation, saving wasted work. But efficiency is only one sort of scale we're interested in. People scale matters too. And of course, it's not a surprise that thinking hard about API design can also help with making that API easy to use correctly. for example, here with some thought, we now have coroutine parameters that work just like the rest of the language, and we don't have to worry much about Stack Overflows. Thank you for all your time today. Happy to take questions now, discuss later, anything like that. Questions? Yep.
So, under the rule of call is always serving the caller, meaning that when canceled, it goes immediately to destructors, it never resumes from suspension. How does that impact how you write the coroutine? For example, the first example I can think of is the coroutine code grabs a mutex lock, it gets canceled, destructors.
Yeah.
It's like, do you have any like design guidelines for avoiding that type of scenario?
Yeah, the question was, how do the rules around cancellation affect how you have to write code in your functions to deal with the fact that you might just suddenly run destructors and then stop running? One thing to note there before answering it is that unlike the common arguments about exceptions, this is marked at the call site, right? Co-await, co-yield, that's the only place this can happen, right? Only when the coroutine is suspended. So if you have thoughts about what I'm about to say, if you have feelings about exceptions, then remember that. The answer is it's just like exceptions, right? With exceptions, you might just stop running if you call the wrong function. Let me restate that. You might just stop running when you call certain functions, right? And it's exactly the same techniques. You need to use Destructor. It's destructor-oriented programming, right? You need to use, I hate this acronym because it's so hard for me to say, but you need to use RAII, right? And that's actually like a pretty good style in general. At Google, we don't use exceptions, and so people have a lot of feelings about this. And still, in the 16 years I've been at Google, RAII has become much, much, much more common in core APIs because it makes code much easier to read, right? It's set up, you know it's gonna get torn down. You don't have to write go to fail error paths, right? We all know the advantages of that. And so it's already a useful pattern. And so if you use that, you're good, right? That's what it comes down to. And with your mutex case, well, you need to use an RAII mutex type like abcel mutex lock in my examples. And you need to restore invariance somehow, but that's up to you, right?
First, I want to say this is a very great talk.
Oh, thank you.
And I want to comment that there is a way to have a sort of make a cleanup function and validate that it is being called once, like either directly or through a scope guard, and there is no use after the function for this variable. Otherwise, if someone tries to do something like this, they will get static assert. There is a way to validate it with stateful metaprogramming, and so you can have like async Destructor.
Okay, I think I would love to hear more about that offline, if you don't mind. Come get me later. Yeah. Anybody else?
So I would assume with your design choice regarding cancellation, you cannot have a coroutine reject the cancellation request.
The question is, you said you would assume that with the cancellation rules, the coroutine can't reject the cancellation request.
Or shield a portion of itself.
Or shield a portion from cancellation. The answer is yes. Like,
yes,
no, the answer is you are correct in your assumption. The rule is you stop running when you next suspend if you've been canceled.
Should be prepared to stop running at any co-await or
Should be prepared to stop running at any co-await or co-yield that actually needs to, well, any co-yield and any co-await that actually needs to wait for something. There's one little subtlety there, but we can disregard that for now. If you want other semantics, you can absolutely build them, but you need to be explicit about it. I didn't talk about it in the talk, but for example, one of the things your destructor can do is schedule some async cleanup work to run in a unowned context, like a context where you know it will never be canceled. So some other talk.
It happens detached from the main coroutine you were canceling.
You need to detach some cleanup work, that's right. And it can be async cleanup work, that's totally fine. But you need to play games like, okay, here's another bug we see with cancellation at Google. Often when canceled, it will be like, okay, I need to do some cleanup work that might take a while. I will detach some cleanup work. I think that is it's not necessarily wrong to do that, but it often is wrong to do that. And I would like to make it something that you have to explicitly choose to do. The reason it's often wrong is you get dangling references, all the problem with unstructured concurrency we talked about. Also, you get arbitrarily much cleanup work building up. If you're doing 10,000 hertz of RPCs and even 100 hertz of them get canceled, now you've got 100 hertz of incoming cleanup work building up, but nobody waiting on it, and maybe some backend that you're using to clean up work gets overloaded, and now suddenly you run out of memory because you got too much cleanup work. You don't have any pushback on the cleanup work, right? And so I think that can be a harmful pattern, so I definitely do not want that to be the default. But you can absolutely build it if you know what you're doing. Yes?
Okay, I'm pretty sure I got this straight in my head, but it's like, so for cancellation, you're only doing it at like CoStar boundaries. So that means you're definitely structurally avoiding like the thread kill problem.
Yes. The question was, if I may restate, why is this different from pthread cancellation, which is a famously bad idea? Is that correct?
Yeah.
And the answer there is because I'm not a pthread expert, but as I understand it, there's what appears to be a random set of functions that are cancellation points for pthread, where you may just stop running suddenly.
Boom.
It's basically the same answer as I gave about exceptions.
Yeah.
That is sort of harmful because you can't see it at the call site. Same arguments apply to exceptions. Like if you know what you're doing, you get it right. You know.
One thing is pthread cancel actually does run destructors.
Pthread cancel does run in destructors, correct, and that.
Unlike pthread kill.
Sorry, I didn't understand that cancel and kill were different things. Kill doesn't run destructors.
Kill does not.
Oh, that's terrible. That's terrible.
Yeah.
Don't do that.
Don't do it.
Okay.
It's such a thing.
Okay, but pthread cancel is also seen as a famous mistake, I believe, by many
It's
people.
gotta
Let's
be
say.
so cooperative with everything.
Yeah, exactly. But here it is marked at the call site. Co-await, co-yield may be canceled or may stop running. Let's say.
So I know like my transaction boundaries are.
Exactly.
Yeah.
Everything between a suspension point is a critical section in the sense that it all or none of it runs, right? And that's good. It's atomic in that sense. Yes.
A little earlier, you discussed the possibility of detaching cleanup work
Yeah.
to like an unowned context.
Yeah.
And a problem being that there may be like an arbitrary number of cleanup tasks that get scheduled
Yeah.
and start wasting time and resources. Given the cancellation method is all about invoking destructors without resuming from suspension,
Mm-hmm.
how is that still a problem? Can that still be a problem? Because if you can't call cancel, that means you're effectively invoking the destructors of everything that's below from that point for all the scheduled coroutines that are awaiting whatever.
Yeah.
Right? Is that ever a problem in that context? It's like an eager.
You're saying that when you this is what we're discussing, right? With a eager future destructor, it may run arbitrarily many destructors as it deals with the long chain of stuff that whatever root coroutine was doing, right? Is that ever a problem? I don't know. Like it would also be a problem in any other cancellation model I can see, right? But do you have a specific example in mind that I think I need this to be more concrete.
No, it's just that you brought up the potential problem of an arbitrarily long list of cleanup tasks to do, which may consume time.
Yeah.
And this cancellation model, it might not run into Stack Overflow problems, but it still takes time to run all of
yeah, I see. Yeah, that's true. And that's why, as we talked about earlier, let me restate for the microphone. I talked about how we won't get Stack Overflow from the destructors if we use structure concurrency and everything, but still you may have arbitrarily much cleanup work to do, which does take wall time and CPU time. Yeah, absolutely. So this is why destructors should be fast. And if you write cancellation handlers that use a bunch of CPU time, well, you're definitely going to use CPU time to deal with cancellation. And yes, you'll probably be doing it on some network thread or something. So try not to do that, or have sufficient parallelism in your network threads.
That is enforced by guidelines outside of the
Yeah, that can't be. I don't see any way, like this is extra textual in a sense, right? I don't see a way that you could do anything about that here. But let me know if you have ideas, please. Yes.
Okay, so you mentioned the rule that single stack shouldn't have more than one like coroutine stub in it or whatever. So I wasn't sure. Is there a way to enforce this? Compile time, runtime, and is it tenable even in a world?
Yeah. This is a very good question. The question was, my rule is that one coroutine should never run on top of another one on a single thread. Only at most one stack frame to a running coroutine. But how do I enforce that? The answer is, I didn't go into this here, but the ecosystem here is closed. you don't get access to coroutine handles. You can't call resume directly. So a user can never do this. Like the resume function can never be called by a user, which means, thank you, using public APIs, you can never get access to a coroutine handle to resume it yourself, and all of the other functions do the right thing. There's not actually that many places that you actually need to explicitly resume a coroutine. It's basically just in bridges from other ecosystems, or like when an RPC reply comes in, that kind of bridge. And you're never in a coroutine context there, right? You're on an RPC thread in some event loop reading replies from the network. You're not already in a coroutine. So it works out pretty well. But the closed ecosystem is the way that you get this for free. And yeah, there's, I think in debug builds, there's checks that make sure I don't mess this up.
Oh, okay. My concern is that inside my coroutine, I just call into some other library, and that other library just decides to call something.
In your coroutine, you call
invoke a coroutine.
Oh, I see. Yeah. The question was, I call another function, and that one co-awaits. You can't do that because of the function coloring, right? The only way that you can legally do that. All right. Let's say you've got coroutine foo and it calls coroutine bar.
This leads to function coloring.
This leads to function coloring, yes.
Yeah. In order to keep just one, you have to create the chain of co-awaits.
That's right. There's nothing you can do with a co-object except co-await it. And so, and it's marked no discard, right? So
as code evolves, I just call a library function that's currently totally synchronous, and it's a new version of it.
But then it would change.
You change the signature. This is why it's no discard, right? You'll find the call sites.
Someone else would have to change their return type.
Yep.
Yeah. It's true. If you change the color of a node here, it has to propagate upward. That's the basics of function coloring. I happen to think function coloring is a good thing if the compiler can check it. And in this case, it can. So hooray.
Okay, thank you.
Yes.
When you mentioned closed ecosystem, did I understand correctly that the public interface, even if it supports asynchronous tasks, none of the public interface is actually a coroutine? It doesn't escape. It doesn't let any coroutine handler escape.
What I meant by a closed ecosystem is basically that you can't get a handle to the std coroutine handle. You can't get a copy of the std coroutine handle. Everything has to go through public APIs that I control. So for example, the common question that comes up after I say closed ecosystem is, what if I want to call from a blocking function? The answer is there's an easy bridge to do that. It's a function called wait for coroutine. And that one, as Jeff was asking earlier, like it takes a co-object directly. So it's literally, if you want to call a coroutine foo, you say wait for coroutine foo, blah. Like it's pretty easy. And that returns the result. It returns a status or result, abseil status or result. So an error or the result. And the error can be I was canceled or I hit my deadline. But that's how you call into the ecosystem. There's similar ones from other internal async ecosystems at Google and from the stubby RPC handlers at Google, that kind of thing. And each one of those knows to do the right thing with the other form of cancellation. Like in a stubby handler, an RPC handler, if you call a coroutine, it knows to propagate cancellation from the RPC into the coroutine and do the right thing there. But you can never call resume directly, which means you can never get the stack frame build up because all these bridges do the right thing.
So does that mean all the public functions, the public interface is not coroutines themselves?
No, I mean the event wait, for example, is a public API that is a coroutine. What it means is you can't write your own awaitables without using one of these other public APIs. So for example, if you wanted to make an awaitable for some other system, probably you would use this event class to do it. That would be the easiest way to do it, to say, okay, now I'm done. Please resume when appropriate. If you want to do it more efficiently, you have to implement an interface I haven't shown here that deals with the stop token-like stuff that we talked about.
Okay, so they can be coroutines, but they only ever return the libraries awaitable objects.
That's right. There's a closed set of awaitables, I think is probably the most precise way to say it.
Okay.
Yeah.
So you never, in addition to the handle, you never exposed the raw promise that would let you.
Yeah, and don't expose a promise either, exactly, yeah. Anybody else? Yes?
Can you explain a little bit more about the integration with RPCs?
What would you like to know in particular? I can talk all day about that. Yeah.
Okay. So I imagine if you have a method, it will generate with the code
Oh, I see. Bindings for RPCs is what you're asking about. Yeah, I actually cut part of that from the talk.
Okay.
The question was, how does integration with RPCs work in terms of like what the local function looks like that is exposed over the network? Yeah, it's the obvious thing. The semantics for, let's talk about gRPC because that's public, right? The semantics for gRPC is you get one message in and you can return an error or another message, reply message, right? And so that's the obvious way. It's a absil status or reply message. That's the, is everybody here familiar with status or? Probably not, but it's like stood expected, but not. It's just, it's either the type or an error, yeah? It's a variant for either the type or the error. So the return type from an RPC binding function is because it's a coroutine, status or because it might fail, reply message type, yeah? And then the name of the method, and then the input is a grab bag of random features that gRPC provides you as one parameter, and then the request message as a reference. And then actually where this works out really well is something I haven't talked about at all, but it's streaming, streaming coroutines, things that can co-yield. I'm not using the term generator because they can also wait for things. They're not synchronous. I've got a whole thing for that, and it works out super well for streaming RPCs. I have never seen an async streaming RPC API that was not a pain in the ass. It's actually pretty good with coroutines, so that works out pretty well. And it's the obvious thing. It returns a stream of messages followed by exactly one status, and that status is okay if you provided all the messages. Otherwise, it's an error if it may have been truncated. And you can also accept streams as a parameter, but that's a whole other talk. Streams bring up other issues. Anybody else? Okay, thank you everybody for your time.